Hey, Prasant, you're not supposed to be on my call right now. We're supposed to be in person. Okay, I will start class now. Okay, so the first question is glyceraldehyde 3-phosphate dehydrogenase catalyzes the following reaction. So it's G3P plus inorganic phosphate plus NAD plus goes to 1,3-bisphosphoglycerate plus the H plus NADH. So in a spectrophotometer, NADH absorbs light at 340 nanometers, and NAD plus does not. So the Beer-Lambert law relates the absorbance of a solution to its concentration and states that the absorbance equals to EC times the pad length. So you guys just memorize this equation. I know this looks really overwhelming because it's a lot, but the questions are just basically simple algebra. So where A is the absorbance, E is the molar extinction coefficient, and C is the concentration, and L is the path length of solution in spectrophotometer. In all the calculations that follow, assume L equals to 1. And the example is all measurements were made in a cuvette with a 1 centimeter pad length. So L can effectively be disregarded, although not its unit. So the molar extinction coefficient for NADH is 6,300 liters per mole times centimeter inverse, or this, or this. So the molar extinction coefficient is the absorbance of a 1 molar solution in a 1 centimeter pad length cuvette. The molecular weight of NAD+, which is given to us, is 663.4. So also remember that dehydrogenase is an enzyme, and so usually what it functions to do is reduce NAD+ to NADH. So this is like the continuation of this problem. In a 1 milliliter cuvette, you mix 0.2 milliliters of 5 millimolar NAD+, 0.2 milliliters of 0.2 molar pyruvate, and 0.2 milliliters of 0.1 molar CoA, 1.2 milliliters of suitable buffer, and 0.2 milliliters of a solution of purified G3P dehydrogenase. You mix the solution and place cuvette in a spectrophotometer and follow the absorbance at 340 nanometers. You measure a rate of increase of absorbance of 0.45 minutes inverse. The enzyme G3P dehydrogenase preparation you used in the assay contained 2.91 milligram of protein per milliliter. So our first question here is, how much NAD+ should you weigh out to prepare 1 milliliter of a 5 millimolar solution? So I know that was kind of a mouthful. Does everyone understand? Get that? And I'm going a little too fast with the problem. I'll just continue. Okay, so we have to convert the 5 millimolar solution to molar. So, you know, milli is times 10 to the negative third power, right? So it's going to be for 1 molar. So this is what it's going to be. And 1 milliliter is equal to 1 times 10 to the negative 3 liters. And so you just like convert it and you get 5 times 10 to the negative 6 mole. And so what we're trying to find is NAD+. Okay, so we're supposed to see how many grams there are going to be in NAD+. So you do molecular weight times mole. And it's going to be 663.4 grams per mole, which is the NAD+ that was given to us in this problem. And you multiply it by 5 times 10 to the negative 6 mole. And it's equal to 3.32 milligrams. I just converted from gram to milligram. Does everyone understand? Does anyone have any questions before I move on? Okay. I will move on to question B. So this one is, what is the absorbance of a 0.09 millimolar solution of NADH? So this is our equation, which was stated in the problem before. So 6,300 this. So this is our E, which was given, it was given here as a molar extinction coefficient is our E. So that's what it was. And then you basically multiply it by 9 times 10 to the negative fifth molar, which you get from this, the solution of NaDH. And you multiply it by the path length, which was 1 centimeter. They gave it to us here. Okay, so you do that and you get 0.56 equals to the absorbance. So the absorbance is unitless. So if no one has any questions in regards to that, I will move on to question 1C. So this one is calculate the rate of production of NaDH in this assay in units of micromoles per minute. So this is our change of A, which is equal to 0.45 minutes inverse. So we get this from the problem here. So you see that it increases the absorbance to 0.45. So since it increases from a 0 absorbance. If that makes sense. So that's why our A initial will be 0. And then our AF final, since it increases to that, will be 0.45 minutes inverse. And the reason why it has units is because this is not just the absorbance, it's the rate of it, the absorbance. And so this is A to final absorbance minus initial absorbance over minutes. And so you just plug the numbers in, the final minus 0 over the units, and you get this. So ECF times L, this is what A is equal to, the absorbance. Does that make sense to everyone? A equals to ECL. Yes, no? Okay. So this is over minutes. And so the third step we do is that the concentration, the final concentration over minutes equals to 0.45 minutes inverse divided by E times L. So you basically have to rearrange this equation to this. And you get 0.45 divided by 6,300, the molar extinction coefficient, multiplied by the 1 centimeter, which was the path length. And so you get 7.14 times 10 to the negative fifth molar over minutes. We're not done. I'm just going to wait a little for you guys to write. Okay, I'm just going to move on. So I still have not finished question C. So the volume of the solution, the total volume of our solution is this. So we get this from this little part here of the problem given to us. So you add that together, you get 2 milliliters for the total volume. And so you have to just convert it from the final concentration per minute to this, and then to micromolar per minute. So basically we got 7.14 times 10 to the negative fifth molar over minutes. And then you multiply this. And remember, this molar is moles over liters. So you do this, cancel them out, and you multiply it by 1 times 10 to the sixth micromole over minute. So this one is just a unit. You know how like 1 mole is equal to 1 times 10 to the 6th micromole. Does that make sense? And so then I get this, 7.14 times 10 to the negative 2 micromole over a minute as my rate. Yeah. One times 10 to the negative. Oh, that's a good point. Let me see. Okay, I think you're right. Yeah, it's supposed to be 2. I'm so sorry, guys. I think the answer key said the wrong thing. So it's supposed to be 2. And so, let's see. I'll get back to you, but I'm pretty sure it's supposed to be 2 also. Don't know how I didn't see that. That means that changes up our whole thing. So it would be 1.43 times 10 to the negative 1 instead, micromoles. Thank you so much for catching that. I did not know how to see that. Okay, so this is going to be 1.43 times 10 to the negative 1 micromole per minute. Okay. Okay, does that make sense? Does everyone know like what she said? Okay. Okay, I'm gonna move on to the next one. If you guys have any questions, just let me know. You can stop me. So calculate the specific activity of the G3P dehydrogenase in this assay in units of micromoles NADH produced per minute per milligram protein. So we're not gonna look at this because this connects to that problem. So basically we're gonna do 1.43 times 10 to the negative 1 micromole over minutes, which is our rate. And then you're going to divide it by the 2.91 milligrams. And we get this from the problem because this is our total grams here of the assay of G3P dehydrogenase assay, 2.91 milligrams of protein per milliliter. So we do that. And then our G3P dehydrogenase is supposed to be 0.2 milliliters. That makes sense. Okay, so let me just do the math. So it's going to be equal to 0.246 minutes. Okay, so this is going to be, let me write it down here, 0.246 micromoles per minute per milligram protein. So we get the units from the problem. Straight in here. Yeah. So the 0.2 milliliters is basically the G3P dehydrogenase's amount. Here. Yes. Yes, sorry.
So 2.91 milligrams also supposed to be over milliliters, so the unit can't go up.
No, it's just milligrams. Wait, let me see. No, it is. You're right. I'm so sorry. So milliliters just cancels out like that. I'm sorry. There was like stuff that was wrong on the answer key, and then kind of did it last minute. Okay. Does that make sense to everyone? So if no one has any questions, I will be moving on. Okay, so this one is more conceptual. It's not any, like, there's no math. People on my live stream, you're not supposed to be on it, unless if you have a reasonable excuse, so can you please leave? Thank you. Okay. So number 2 is you are a doctor of an 80-year-old man in a nursing home. Blood analysis shows that the patient's blood glucose is extremely high, so it's supposed to be 20 millimolar per liters. The healthy range is 4 to 8 millimolar per liter. Your first suspicion is type 1 diabetes. So you're gonna know, you guys have to know what like the C-peptide is for this exam. So you order a C-peptide analysis, which shows that the patient has a high blood concentration of C-peptide, 2,100 picomole over liters. The healthy range is 260 to 1,000 picomole per liter. Based on the finding of greatly elevated C-peptide concentrations, you conclude that the patient has type 2 diabetes. So describe how insulin is produced from an inactive precursor. So pancreatic beta cells produce inactive precursor proinsulin. And then proinsulin undergoes a proteolytic cleavage and forms insulin and the byproduct C-peptide. So the C-peptide is originally linked to insulin in the proinsulin form, but it's going to be released during cleavage. You guys get the concept a little? Okay. So C-peptide kind of is like works with insulin. It's like directly proportional to it, if that makes sense. I'm gonna like flip the page because it's not done. So this generates the hormone insulin. Do you guys want me to draw like a little chart out of how the steps, how it goes for this what I just explained to you, the concepts? Okay. So for 1A, it's supposed to be like, so you're supposed to know that beta pancreatic islet cells, I believe. So they release proinsulin. And then proinsulin splits into two, produces insulin and C-peptide. And then this just like leaves. It'll make a little more sense once I go over question 2B also. Okay, I'm gonna move on from this. Okay, so for 2B, explain how high blood glucose and elevated C-peptide levels are a diagnostic for type 2 diabetes rather than type 1 diabetes. So C-peptide levels indicate endogenous levels of insulin, right? So these insulin levels are a response to glucose intake or blood glucose levels. So when glucose is raised in your blood, insulin will come to lower it. It's kind of like homeostatic to balance it out. So patients diagnosed with type 1 diabetes produce lower levels of insulin than normal, meaning that their C-peptide levels are also low. Because this patient has a high C-peptide level, we can conclude that insulin production is greater than usual. So the patient must have type 2 diabetes rather than type 1 diabetes. Does that make sense? Everyone. You have a question? This is our last problem of the day. I'm not going to start on question 3 because it's kind of long and it has more concepts to it. So if you guys have any questions or want me to go back to a problem, I can.
Can I look at number 1B?
Yes. Everyone's good with this, right? Or I can come back to this. Okay. So 1B is just really simple. It's just A equals to E CL. So it's just
80%. Oh, is it just the?
You just plug in, yeah.
Okay.
Yeah, no problem. Have you guys learned this in class yet? Or?
We learned this last year.
Oh, last year.
Biolab.
Oh, yeah. Okay. I'm gonna stop the recording.